So I want to say something about differentiability of O-minimal functions. So suppose f is some definable function from an interval to the real numbers. And then we do the following thing. We define f left to be the limit t less than x of the following quantity, so to expect, and f right is the limit as you approach x from the right. And both of these guys take values either in the reals or plus or minus infinity. So now note that FL and FR so let me do the following thing. So if we look at this function, so g of t equals f of x minus f of t over x minus t, where x we think of as fixed, and for each x, this is a definable function of t. So this is definable. And so as a result, the limit as t goes to x from, I forget the notation, from like above or something, or from below. So it's increasing. Anyway, so this limit of g of t exists. Right? Because we showed that any definable function in O-minimal structure, you can actually break up into intervals where it's piecewise monotonic on each interval. And so any monotonic function is going to have a limit. So in particular, FL and FR sort of exist everywhere. Maybe plus or minus infinity, but they do exist. Okay? They might not, Yeah. All right. So now let's prove they actually behave pretty nicely. So the first claim is that FL of x equals infinity for only finitely many x. This is a sort of exceptional case. Alright, now since we're working in an O-minimal structure, as always, the points where it's infinity are a definable set. So they're either a finite set or they contain some interval. So by O-minimality, it's sufficient to show FL is not identically infinity. So I'm working with plus infinity here. And similar things work for FR and plus minus infinity. Okay, so assume it is. So assume not for the sake of contradiction. Well, assume not, double negative is confusing. So assume it is plus infinity. And for simplicity, or concretely, let's say that I contains some closed interval AB. Okay. Okay. And let R be the slope of F along AB. Okay, and so now we can replace f by f of t minus r of t. So that will scale. It will just shift fl and fr down by r. And so it won't affect this property. And so then we can assume f of a is equal to f of v. And also by possibly shrinking the interval, we can assume f is continuous. We know it's only discontinuous and finitely many times. And f on I is continuous. Okay, so f(x) is plus infinity, so it starts. There's a point where it's bigger than a. So now, let's see inside this interval be such that f of c is the maximum value of f. And note that c doesn't equal a or b because it's increasing from a. Okay, but then if we look at f of c, sorry, the minimum is what I want. Now it's increasing at b, so it goes below f. So there is a minimum, but it's not at b. But then f of c minus f of t over c minus t is less than 0 for c less than t, for t less than c. As you approach from the left, your slope has to be negative, and so therefore fl of c is less than 0, less than or equal to 0. And that's a contradiction, so we assume that it's infinity. Okay? Okay, so FL and FR are actually inside R almost everywhere. Okay, so now claim number 2, unsurprisingly, is that in fact these guys are equal outside a finite set. Okay, so outside a finite set, f prime actually exists. So what's the proof? So if not, then on some interval j inside I, FL, FR are continuous, and nowhere equal. Because again, if they're not equal definable, so the usual stuff. And so we'll log, by flipping f or something, we can assume that FL is less than FR on J. And so by zooming in further, shrinking J further, using a result from last time, there exists some number C such that FL is less than C, is less than FR. Or if you want their continuous monotonic functions, you can get C that way. That's sort of not hard. And so now again, replacing F by F minus this line, we can assume C equals 0. So now FL is less than 0 and FR is bigger than 0. But now FL is less than 0 implies F is decreasing. And FR is bigger than 0 implies F is increasing. Contribution. Alright, so corollary. F prime of x exists outside of finite set. Where F prime is the usual. FL and FR when they agree. The nice thing about this is we can do it over and over again. So corollary number 2, for all integers R, F is CR, R times indifferentiable on I outside of a finite set. Okay? What's really nice, and of course we can also shrink even further and sort of say that we can break I up into finitely many intervals, on each of which F is CR, and each derivative is a fixed sign or something like that. 0. So you can sort of get really nice about it. And so this is true automatically for sort of all polynomial structures.
Is it C infinity?
No, or at least I don't think that's known. I know you can make it non-analytic. I'm pretty sure you can make what you said not true as well, but I haven't checked. Okay, so I want to talk about sort of the main structure theorem for definable sets and no-minimal structures, and that's cell decomposition. And so this is, we're sort of getting really close to the stuff we needed to make the Piliborki theorem work, which is secondly parameterized by these sort of nice functions in a uniform way. So cell decomposition is really the way to formalize that. And so we define K cells in Rn for K less than n are defined as follows. We define inductively. So first of all, a point in zero-dimensional space is a zero cell. Secondly, if X and Rn is a K cell, and F X to R is continuous and definable, everything is definable, then if you look at the graph of F on X inside m plus 1 dimensional space, this is also a K cell. Okay. Moreover, if you have two functions, continuous and f is less than g on x, then if you look at the set of points Ta, where t is an x and a is between f of t and g of t, then this is a k plus 1 cell. Okay? And so now inductively, you can define cells, K cells, Rn in general. So, you know, in 2 space, for example, the typical 2 cell looks sort of like this. So 1 cells in 1-dimensional space, just open intervals, and then 2 cells in 2-dimensional space, you take an open interval, you take 2 functions on it, and you sort of take the space between them. That's a 2 cell. And then if you want a 2 space on 3, a 2 cell in 3 space, for example, you just take this guy, take any continuous function on it, and you graph it. And likewise for follicles and so on. And if you want a 3 cell in 3 space, you take 2 functions, and you have sort of a weird, very skewed sort of cylinder kind of thing. Okay? And so you can also, I won't write it down, there's a notion of smooth cells, where instead of f being continuous, you require f to be smooth, and you can prescribe what level of smoothness you sort of want to have. Okay, so now a cell decomposition of Rn maybe I can also point out that you're allowed infinite things as well, right? So if I had no top, this would still be a cell. So maybe it's better if I sort of, I don't actually mean this, I mean union plus or minus infinity for all of these. Okay. So a smooth cell decomposition of Rn is, so if m equals 1, it's a partition into finitely many open intervals and points. And in general, for n bigger than 1, it's a partition of Rm plus 1, of Rm, sorry, into cells. So to finitely many cells which are disjoint, such that if you look at the projection map from Rn to Rn minus 1, and you look at the set of projections of your cells, okay, then this is a cell decomposition of Rn minus 1. And what is it saying? It's saying that for any 2 of these guys, either the projections are disjoint or they agree. Okay, so it's sort of a nice, a nice way to think about it is if you look at R2, then where this is, let's say, minus infinity and this is infinity, and I've scaled it down for size or whatever. This is not a cell decomposition, right? This is bad because these two agree. Whereas something like this is a cell decomposition. So we start a cell decomposition downstairs, and then for each cell, we sort of lift that into a cell decomposition. Okay, so in some sense, in a very concrete sense, a cell decomposition of Rn plus 1 is like a family of cell decompositions of R, parameterized by a cell decomposition of Rn. Okay. Okay, so the main theorem for cell decompositions is X and Rn is definable. And then Rn has a cell decomposition compatible with X. So we can write Rn into a cell decomposition such that X is the union of finitely many of the pieces, finitely many of the cells. Okay? Which is somehow as simple as you could hope to get. Okay, questions about the statement? So I'm not going to give the full proof because it's kind of long and arduous, but I want to give sort of the idea for it. We've done in some sense the hardest work already, which is the work with functions of one variables and one cells in two space somehow. But so there's something to be done to make the induction go through, but so I want to give a sketch of what happens. Okay, so suppose that, first of all, X is in R2. Let's do the n equals 2 case of this theorem. Then recall that if X is in R, if A is in R, XA is the fiber over X. So there's a set of P's such that TA is an X. So it's a fiber over A. Okay, so we sort of dealt with it. We proved this theorem in the case where X is effectively a one cell. So in the case where X, the fibers, these XAs are finite for all A. We showed they were uniformly finite, and we showed in fact there's a graph of finite many functions, which if you sort of look at that, immediately implies there's a one cell decomposition of X compatible with. So in this case, the problem is that these XAs could be finite unions of intervals. Right, so that's the concern for us. And so how do we deal with that? Well, what we do is we let YA be the boundary of XA for each A. So we're recording sort of, if XA is a unit of open intervals and points, we're recording both the points and the endpoints of the intervals. And then Y is as the union over A of sort of, well, so Y is just glue all these together, TA where T is in YA. And now all of a sudden, y is a definable guy in 2 space, which has finite fibers. Right, so y is the kind of guy we're used to dealing with. So then, by sort of last class or whatever, we didn't label the theorems. By last class, we can sort of decompose R into finitely many intervals. And then union some points, finitely many points, such that on each interval, y is the graph of finitely many continuous functions which don't intersect. Such that on ij, y is the union I equals 1 to, let's say, mj of finitely many functions fi. From imj, from ij into I. Right? Okay, so now the picture is what? So on a given interval, let's say this is ij. What's y? Well, we have finitely many continuous functions giving us the boundaries here. Right, so where these guys, we can also insist are strictly increasing. We can just record the intersection points, break up further. And so what can x be? Well, x is only finitely many possibilities, right? X is sort of finitely many pieces which x either does or doesn't contain. It sort of either contains each of these open intervals or not, either contains these points or not, and so forth. And each one of, so, there's like piece, break it into pieces q1, q2, q3, q4, where each piece is either a point or an interval, right? And so now, the points in ij where x contains any given piece is a definable thing, so it's a finite union of intervals. So by breaking up further, we can sort of restrict it into pieces where we sort of know exactly which pieces x contains, and so we know exactly what x is. Okay? Okay, so I don't want to write all that down, but we can sort of break up into more pieces, such that on each guy, x sort of contains one of these guys. And so the cell decomposition becomes the resulting intervals down here, and for each interval you sort of have these cells that we're taking, together with their boundaries. Is that sort of clear? Okay, I don't write down the argument in full, but that's sort of what happens. The key is this sort of boundary operation reduces us down from k cells to k minus 1 cells, in which we're sort of good. Okay, so even more briefly, I want to sketch what happens for n equals 3. Now x is in R3. And now, so the first case is the projection of x into R2. So now this is definable, so we know that it can be broken up into cells by induction. So the first case is this is a union of 0 cells and 1 cells. Okay, but in this case, we've sort of in some sense already handled, because the 1 cell is just R. It's parameterized by R. And sort of the fiber over a 1 cell is just R squared. Now again, we reduce the 2-dimensional case. So this sort of reduces the 2-dimensional case. Okay, so you can assume the projection of x, the new case where the projection of x is all of r squared. So now again, what we do is now for a in r squared, we can define xa as before, and then we define ya is the boundary of xa, and y is the union of a cross ya, or ya cross a, I guess the way I define it. So we do the same stuff as before. And now y has finite fibers, so these ya's are all finite. So now the ya are finite, and so by almost the same argument as before, we can show that they're uniformly finite, uniformly bounded. There's some absolute bound for these ya's. And then again, we stratify y by sort of these values. And so the claim reduces the sort of only new part of the argument the main new part is we have to show that if f from r squared to r is definable, then f is continuous away from a union of one cells. Anything away from a union of one cells we're fine, because it reduces the dimensional case. And so the point is we can define these functions f as before by looking at the minimum of ya and the second minimum and so forth. But we need to know if these guys are continuous, and that doesn't quite follow like before. So we need like some minor new argument for this. Okay. So let me explain how one does this extra step. So by homonormality, it's enough to show that f is that if you have a function f on I cross I mapping into R, then it's somewhere continuous. Okay. So what I really should be saying here is by homonormality and cell decomposition for the n equals 2 case. Because we know that if this is not true, then it's not true on some set. And if that set is not a unit of one cells, must have a 2 cell, and then that 2 cell contains an open set, so it contains a small box. And so this sort of lemma, replacing 2 with n, is sort of proven interweaving with this guy. You sort of prove the n equals 2 case with this guy, the n equals 2 case here, that gives n equals 3 case here, that gives a 3 case here, and so on. Okay, but this is the main claim. The only reason more difficult than before is before we use this business where if you're increasing and you're onto, then you're continuous. You don't have quite that anymore. So now you do something very similar. So what you do is by zooming in, by shrinking I, we can assume that f of xy is continuous and strictly monotonic, let's say rho log increasing, in each variable. Because we know that, guys, every definable function is continuous in each variable almost everywhere. And so then, we have our I cross I. For each point here, there's finitely many exceptions. So we get a one-cell decomposition, and so we sort of go away from there. That we're continuous everywhere. So this sort of follows from the before. Okay, so then this guarantees that f is continuous, actually. And so then what you do is you sort of have this map f into r. Let's say this point maps to this point, and now take an epsilon neighborhood. Epsilon, this is minus epsilon, say, and we have to show its inverse image contains something open here. Now f is continuous in everywhere, so f is increasing in each variable. So what we can do is we can look at this point, and then first we can go out to a certain amount where f doesn't change by more than epsilon over 2. We can do that. And then for each of these points, f is now continuous in the other variable, and so now we go another epsilon over 2. We have this sort of name. We have a point. We have points like this, where f of each of these 4 points lands inside this neighborhood. Okay, but now f is strictly monotonic, right? So everybody here is between this point and this point. So it's between 0 and epsilon, shows 1 for sure. And the same for the other 4. Okay. Thus we establish this, and then sort of get the rest of it here. All right, that was rather vague, but I just hope to give you sort of the basic gist of the argument. Nonetheless, are there any questions about this sort of sketch? All right. Okay, so that's basically all I wanted to say about all minimal stuff, except for now we'll list some examples. This is all I wanted to say of the general theory. To sort of what we need for the Pili-Wilkie theorem to go through is essentially this. Sort of this allows you to take any family and break it up into reasonable chunks. They do need some strengthening, so sort of strength. Let me just mention the strengthening needed, and it is it's not sort of fully obvious. So the first thing they need, so this is for Pili-Wilkie. The first thing we need is smooth cell decompositions. Or maybe smooth usually means C infinity, I guess. I just mean CR cell decompositions. Right, because our argument requires Taylor expansions to arbitrary precision. So we need something like this. And this isn't actually any harder than anything we've done so far. Just sort of keep zooming in to make things smoother. And things work out. So that's not a major problem. So let me sort of say more or less easy. The second thing they need to make their argument go through is we sort of parameterize things in families, and we need to know that the derivatives of our functions, our parameterizing functions, don't sort of go crazy. They don't get too big for the argument to fail. So before we had things being compact, then we knew things didn't go crazy because of compactness. If we do things in generalities, we should be more careful. So we need sort of uniform boundedness of derivatives. Okay? So somehow they have this idea where you not only record cells, but you also record parameterizations of these cells. It's sort of easy to see that every cell can be parameterized with a disk of the appropriate dimension, just by definition and induction. And so they wanted to show that in fact you can get these functions to have uniformly bounded derivatives. Which is sort of a combination of these arguments and some more being careful. So I don't really want to go into that, but that was something else that was important ingredient to their arguments. Okay, what I want to do now is list. So next class I want to sketch a proof of the homogeneity of at least one structure. I feel like we should go into at least once. But right now, let me list sort of some examples of homonomial structures. And I don't know that many examples, so I'm basically going to tell you all the ones that I know. Okay. So the first one is a structure that's referred to RSA, which stands for semi-algebraic. And this is, guys, defined by the reals, the less than operation, and you add addition and multiplication. So not that nowhere in our theories we require that our structures be closed and with addition and multiplication or anything like that. You can, all we did was less than, or off with erasers. And people do study structures that don't form rings. Okay, but this is sort of the basic one. And what I mean when I say we have plus and times, what I mean is that we contain the graph of addition and also a multiplication. Both of these graphs inside are exactly the same. Okay, so now one thing I want to point out is if we look at the structure given by, I was telling you just the complex numbers, we don't include less than, so it's a bit of a different object. And we give addition multiplication here. So we can still play the same game, right? We sort of add these two graphs and we see what can we define from these guys. And so what does this give you? Well, it's sort of not hard to see. It gives you all algebraic varieties. Right? They're all combinations of these kind of things. But then we also have projections. So we have sort of all projections of algebraic varieties. But in fact, what this gives us is just constructible sets, i.e., sort of Boolean combinations of algebraic varieties. So this is Chevalet's theorem. I'm going to misspell Chevalet. I'm sorry for that. Frank, I feel like you would likely know if this is correct.
I think the last A should be an E.
Should be an E? Okay. Thanks. So yeah, Chevalet's theorem is if you take any algebraic variety in Cn and you project Cn minus 1, you get not necessarily an algebraic variety, but a Boolean combination of algebraic varieties. Right? It's like xy equals 1 projected down doesn't give you an algebraic variety, it gives you the line minus the point. But that's sort of as bad as things get with the complex numbers, and it's because the complex numbers are algebraically closed. So things are kind of nice. On the other hand, that can't be the case over here. So in fact, if we look at the structure and we remove less than, we can get it back immediately just with addition and multiplication. The reason being that x is less than y is equivalent to there exists z with x plus z squared is equal to y. Or I guess x is less than or equal to y is equal. Okay? And this is something definable just with plus and times. Right? So automatically, if we look at algebraic variety in 3 dimensions and project down 2 dimensions, we recover the graph of less than. And so, okay, so if you just sort of great variety sort of in the reals, they aren't closed on a projection, they don't form a structure. But the theorem of Tarski and Seidenberg is that just by adding less than, you've sort of recovered already what you need. So all so any definable, so if X and Rn is definable in the structure of semi-algebraic functions, this is equivalent to X as the union of finitely many xi's, where each xi is defined by finitely many functions being less than 0 and finitely many functions being equal to 0. Okay? So this is recorded usually as quantifier elimination. This is called quantifier elimination for this structure. It basically means that any set you can write down with quantifier using less than, plus, and times, which means what? It means you sort of define a high-dimensional set and project things down. You can already define without quantifiers, just by looking in RSA and writing things down with plus, times, and less. Okay? I'm sorry? Well, these are polynomials, yeah, sorry. Sorry, of course. The Fi and the Gj's are in the ring of polynomials. Okay? And now that this theorem, it has as a corollary that this guy is O minimal. Because if you apply it n equals 1, all you can do is set one-dimensional polynomial of less than 0, and that's clearly a union of finitely many intervals of points. So this sort of, at least to me, illustrates something that omnimality sort of, it's really, we sort of talked earlier how it's sort of really cute, that it's really useful, that by imposing restrictions on one-dimensional sets, you get all these corollaries for high-dimensional sets. And that's true. It's nice to capture things theoretically in that way. Nonetheless, it's not like you've cheated your way out of dealing with the high-dimensional sets. In order to prove something is O-minimal, you usually do it with some form of quantifier elimination. So you prove some strong enough structure theorem in all dimensions, which implies the O-minimality in dimension 1, at which point you can then use this as a tool to prove more sort of nicer structure theorem in higher dimensions. But sort of the starting point is some sort of fairly strong classification theorem for all your guys. Clock is a little. Yeah. The second example of an O-minimal structure, which is necessary for the applications we want, is Rx. So Rx is the structure you get from adjoining addition and multiplication and less than, but as follows, and also the exponential function, the real exponential function. So adjoin the graph of y equal to e to the x. So y, it has to be the real one and not the complex one, because the complex one has infinitely many zeros, and that's sort of not allowed. Right, so, okay, but this guy, ends up being O-minimal. This is the theorem of Wilkie. based, well, I guess it's largely based on work of Tolansky. And let me say one more thing before we end. So this structure is special because it sort of seems like a random structure. You add this one function, you get something all minimal. So it's special in the following way. So another theorem, if S is an O minimal structure, and S contains some function which grows faster than any polynomial, any power of x, I guess, then in fact it contains the exponential. Somehow the moment you step outside polynomial growth, you get y equals to the dx. So it's not sort of some arbitrary structure, it's really canonical in this sense. All right, let's stop here and then we'll give more examples and start this proof next time.